Hi everyone, welcome to lecture number 4 of probability in statistics under GATE DA. So we have seen conditional probability, what is the probability of an event A given that event B has already happened, and then which is equal to probability of A intersection B upon probability of B. And then we rearranged it to get probability of A intersection B, like probability of two events happening together is probability of any one event times probability of the other event given that the first event has already happened. That was called multiplication theorem. Now again, very similar, like going forward in conditional probability and multiplication theorem, we have a very beautiful notion of independent events. So we will see independent events in this and next lecture. So what are independent events? So let's see the definition first. Yep. So the case where probability of E given F has already happened is equal to probability of E. What does it mean? That it doesn't matter that F has happened or not. Probability of E remains same. So you have two events. So for example, throwing a dice. Okay. Let's say E is an event. Again, E is an event of getting a prime number. We know that it is 2, 3 and 5. And let's say F is an event of getting an odd number, which is 1, 3 and 5. Right. So here in this case, when we throw a dice, we know that what is the probability of just event E? It is 1 by 2 because we have 3 cases which are possible. You can get 2, 3 or 5, they are all prime. So probability of happening of event E is 1 by 2. Similarly, probability of happening of event F is also 1 by 2. There are also 3 cases here, 1, 3 and 5. But now, in this case, what is the probability of E given F has already happened? We saw this in last class, right, in conditional probability. So if we know that F has already happened, if we know that 1, 3, 5 was already there, it is sure that it is either 1, 3 or 5. Given that F has already happened, what can be the prime numbers? 3 or 5. Only 3 or 5 are possible. So the probability now, the new updated probability of event E happening, given that F has already happened, is 2 by 3. You can use the formula as well, you will get 2 by 3, right? So now here what happened, see, probability of E initially was what? 1 by 2. But probability of E given F has already happened increased a little bit. So it might increase or decrease depending on the events, right? But sometimes it can remain same also. So if the probability of E given F has already happened doesn't change, it is equal to probability of E only, then E and F are said to be independent. The very common mistake, or the common difficulty which people face in probability is they consider independent events and mutually exclusive events same. Mutually exclusive events are different, independent events are different. Mutually exclusive events don't have anything in common. Mutually exclusive events don't have anything in common. For example, getting an even number and an odd number. These two events have nothing in common. So their intersection is phi or the empty set. But independent events are different. And we will later see in this lecture that they are actually very different. If two events are exclusive, they can never be independent, right? So we will see that. So they are different notion. Exclusive means they have nothing in common. Independent means happening of one event doesn't affect the probability of other event. Like this. Here, happening of F affects the probability of E. So that's why they are not independent. So if P of E by F is equal to P of E, which means that happening of F doesn't change the probability of E, then we say that E is independent of F. Okay. So we can also rearrange terms. So what is probability of E by F? It is probability of E intersection F upon probability of F. We already know this. And it is if E and F are independent, we know that probability of E by F is nothing but the probability of E. Which means that two events are independent if the probability of their intersection, two events are independent if the probability of their intersection is nothing but the product of their individual probabilities. Okay, I just rearrange this. So two events are independent if probability of their intersection is product of their individual probability. See, it is different from mutually exclusive events. In mutually exclusive events, probability of intersection is 0. Right? If two events are mutually exclusive, their intersection has nothing in them, right? So probability of the intersection becomes 0. But here it is not 0, here it is a product of the individual probabilities. So E is independent of F if knowledge that F has occurred does not change the probability that E occurs. So in some cases it will be very obvious that two events are independent. When we see examples, I will tell you, right? So in few experiments or examples, it will be very clear. But just by seeing the problem, you will see that the events are independent. The happening of one event doesn't affect the probability of other. But sometimes it is not very obvious. Sometimes in some experiments, when you see the sample space and the events, it will be not very obvious that the events are independent. And in those cases, generally when you apply the formula and see if the probability of intersection is actually equal to the product of the individual probability, then they will be independent, okay? So we'll see like both examples, like which are obvious and not obvious. Cool. So if two events E and F are said to, so the two events E and F are said to be independent if this equation holds. Two events E and F that are not independent are also called dependent, okay? So if they are not independent, they are called dependent. So let's see an example. Okay, so we are tossing two coins, okay? So the experiment is we are tossing two coins. So we have two coins and we are tossing them. So what is the sample space? Sample space contains 4 outcomes. Either you can get head in both. You can get head in the first and tail in second. Tail in first, head in second. Or you can get tails in both. Right? This is your sample space. Now you are given two events. First event is getting a head on the first coin. First event is getting a heads on the first coin, which means this or this, right? So the event even is what? Either heads or heads tails, right? Event 2 is given as getting a head on the second coin, which means either this or this. Oh, sorry. Yep, either this or this, right? So what is event 2? You have to get in heads on the second coin, which means either you get heads or tails heads. This is your event 2. So question number 1, are these two events mutually exclusive? They are not mutually exclusive, right? They have something in common. This is common in both. They can happen together. Both these events, even in E2, can happen together. They are not mutually exclusive. But are they independent now? Let's see that. So what is probability of E1? Firstly, I will give you the formula notation, right? Like we will just use the formula to find out they're independent or not. Then I will give you the logical explanation as well. So what is probability of E1? There are two events which can happen, and there are total 4 events in sample space. So the probability of just event E1 happening is 1 by 2. Similarly, probability of happening of event E2 is also 1 by 2, since there are 2 elements in it in event E2. Now, what is the probability of E1 intersection E2? So what is E1 intersection E2? We already saw. There is one element which is common in both E1 and E2, which is heads. So the probability of E1 intersection E2 becomes 1 by 4. And here we can see that probability of E1 intersection E2 is indeed equal to the product of individual probabilities. Probability of E1 times probability of E2. Right? So hence they are independent. What does it mean? Ki the happening of second event doesn't change the probability of first event. And similarly, happening of first event doesn't change the probability of second event. It's true both ways. So it is obvious as well. Like, think about it logically. If you think, getting a head on the first coin. Okay, so somebody is saying like you're tossing 2 coins. Let's say 2 individual people are tossing 2 coins, right? So first guy says that I got an head. Now what is the probability that you are getting head? It still remains half, right? So second guy is independently tossing the other coin, right? So it doesn't matter what happens on the first coin. Probability of getting a head on the second coin still remains half. At the beginning of experiment, what is the probability of getting a heads on the second coin? It's half, right? But if the first guy says that I got an heads, but still like the probability of second guy getting an heads still remains half, right? So it's very logical. Like this was an obvious example. So generally, like examples like this, where like you're tossing 2 or 3 coins, then like individual probability of these coins will be independent. Or sometimes when you have a bag, let's say like that's a very standard problem in probability, right? A lot of times it is asked in GATE. So there is a bag which contains n number of red balls, blue balls, and black balls, and you take one ball out of it, and then you take second ball out of it. So if you take the first ball and then the second ball, if you don't replace the ball, generally like the difficult question is you are not replacing the ball again. When you take the first ball out, you place it somewhere else. Then you take the second ball out. In this case, the outcome of the first event, which means the outcome of the first time when you are grabbing a ball out of the bag, actually is dependent on what is happening in the second event, because you might get a red ball in the first event. Now the bag changes, right? So in this case, they are not independent. But sometimes it might be given that when you are pulling balls out of a bag, you are again replacing them back. So you take one ball out of the bag, you see the color, and then you again put it in the bag, and then you again pull out one ball. Now in this case, event E1 and E2 becomes independent, since the configuration of bag remains same. Okay, we will see with examples as well. So this was first experiment. This is second experiment. You are rolling a die. Now this example is not obvious. Okay. So you are rolling a die. So what is the sample space? It contains 6 possible events which are possible. You can get a 1, 2, 3, 4, 5 or 6. Okay. Okay. So basically getting a 2 on the first die, getting a sum. So you're rolling 2 die actually, like there is a mistake here. Since in the events they are talking about 2 dice, so the experiment is rolling 2 dice. Okay. If you're rolling 2 dice, what is the sample space? It contains 36 possible outcomes. You can get 1 and 1, you can get 1 and 2, you can get 1 and 3, so on, you can get 6 and 6. Right? There are 36 possible outcomes, we know. Now event E1 is given to be getting a 2 on the first dice. So what is event E1? E1 will contain 6 events, right? Like 6 possible outcomes. You can have 2 1, 2 2, 2 3, 2 4, 2 5 or 2 6. This is event E1. You are definitely getting a 2 on the first dice. The event E2 is given to be getting a sum of 5. So what are the possible outcomes in this? How can you get a sum of 5? So you can get 1 on the first dice and 4 on the second. You can get 2 on the first dice, 3 on the second, 3 on the first dice, 2 on the second, and 4 on the first dice and 1 on the second. These are the full possible outcomes, which will give you sum of 5. And event E3 is given as getting a sum of 7. So what are the possible outcomes here? 1 6, 2 5, 3 4, 4 3, 5 2 and 6 1. Right? Okay. Now we will see pairwise, like what all events are independent of each other. So this is our sample space. It contains 36 possible outcomes. So what is the probability of event E1? E1 contains how many outcomes? 6 outcomes. So 6 by 36, which is 1 by 6. Probability of event E1 is 1 by 6. Probability of event E2 is what? Probability of event E2 is what? E2 contains 1, 2, 3, 4 items. 4 outcomes. So 4 by 36, 1 by 9. Right? Similarly, probability of E3 is what? E3 again contains 6 outcomes. So 6 by 36, 1 by 6 again. These are individual probability of these 3 events. Now let's calculate the probability of intersection as well. Like E1 intersection E2, E2 intersection E3 and E1 intersection E3. We want to see pairwise what all events are independent of each other. So what is the probability of E1 intersection E2? So how many elements are common in both E1 and E2? Which means you want a 2 on the first die and you want to get a sum of 5. So there is only one element which is common, 2, 3, right? There is only one element which is common. So the probability becomes 1 by 36. Right? Similarly, what is the probability of E1 intersection E3? Let's see the first and third events, which means getting a 2 on the first die and getting a sum of 7. So how many elements are common? So only one element is common, 2, 5. 2, 5 is common in this and this, right? Because you are getting a 2 on the first die and you are getting a sum of 7. So only one event. So again 1 by 36. And what is the probability of E2 intersection E3? Which means you are getting a sum of 5 and you are getting a sum of 7. It is not possible. Either you will get a sum of 5 or 7, right? You cannot get a sum of both 5 or 7. So there is nothing in common in these two. So the probability of E2 intersection E3 is 0. Right? So now which all events are independent? See, probability of E1 intersection E2. Let's see first and second event. Is it equal to probability of E1 into probability of E2? Probability of E1 into probability of E2 is what? 1 by 54, which is not equal to 1 by 36, right? So it is not equal to probability of E1 into probability of E2, which means that E1 and E2 are dependent. They are not independent. E1 and E2 are not independent. And let's see that as well. What is E1? And what is E2? So E1 says you get a, so E1 is getting a 2 on the first die. E2 is getting a sum of 5. We know that initially probability of event E2, which is probability of getting a sum of 5, is 4 by 36. There are only 4 cases, right? 1, 4, 2, 3, 3, 2 and 4, 1. So the probability initially was 4 by 36, well 1 by 9. See, there are no cases in E2, so you cannot get a 5 on the first dice. So if you get a 5 on the first dice, you cannot get a sum of 5 because you will get at least a 1 on the other die, right? That's why you don't have any 5 here. So basically what it means, first die can only have 1, 2, 3 or 4. Then only it is possible. So it is slightly biased, right? Event E2 is slightly biased. It only happens if both the die have numbers between 1 and 4. If any die gets a number 5 or 6, it doesn't happen. So event E2 is not uniform across any dice, right? Because it only happens if you get a 1, 2, 3 or 4. Now event E1 said that, event E1 was, it said that you get a 2 on the first die. You get a 2 on the first die. So initially when you were computing probability of E2, which means probability of getting a sum of 5, you were factoring in all possible cases. You can get 5 or 6 as well, right? That's why the probability was less. It was 1 by 9 only. It is very less, right? But now event E1 said that it is guaranteed that you get a 2 on the first die. Now since it is guaranteed to get a 2 on the first die, what happened? The probability of the probability of event E2 increased. Why? Because it is definite that you cannot get a 5 or 6 on the first die, right? And now like the probability of event E1 will increase. You can see that as well, right? So what is the probability of E1 given E2 given E1 has already happened? It is probability of E1 intersection E2, which is 1 by 36 upon probability of E1, which is 1 by 6. So it becomes 1 by 6 now. It increased. Initially it was 1 by 9, but now it increased to 1 by 6. Why? Because it is given that the first die is giving you a 2. So now the second dice only has to get a 3. Because 2, 3 gets a sum of 5, right? So now out of the 6 possible outcomes, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, one of them is favorable. Previously out of 36 outcomes, only 4 were favorable. But now out of 6 outcomes, 1 is favorable. So the probability increased. And that's why happening of event E1 increases the probability of event E2. And that's why they are dependent. They are not independent. And you get that from the formula as well, right? Similarly, let's see event E1 and E3. So is the probability of E1 intersection E3 equal to probability of E1 into probability of E3? What is probability of E1 and probability of E3? It is 1 by 6, 1 by 6. So product is 1 by 36. It is correct. They are independent. Events E1 and E3 are independent. E1 and E3 are independent. How? The formula gives us that. Because probability of E1 intersection E3 is probability of E1 into probability of E3. But now let's see that as well. Event E3 was getting a sum of 7. Right? Event E3 was getting a sum of 7. So out of all 36 sample space, 6 element passed that. Right? 6 of the outcomes had a sum of 7. So initially the probability was 1 by 6 of getting a sum of 7. Right? These were the 6 outcomes. Now event E1 is saying that you get a 2 on the first dice. You get a 2 on the first. So this is not very obvious. You don't like, by just seeing the problem, it's not very obvious that E1 and E3 are independent. But if you think very logically, see what happens. Initially probability of event E3 or getting a sum of 7 is 1 by 6. And now event E1 is saying that you will get a 2 on the first die. So if you get a 2 on the first die, only 6 outcomes can happen. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5 and 2, 6. And out of these 6 outcomes, still only one has a sum of 7, which is 2, 5. So initially the probability was 1 by 6. Now if you get a 2 on the first die, still the probability is 1 by 6. Because out of the 6 outcomes, only one is favorable. Initially, out of 36 outcomes, 6 were favorable. So probability doesn't change. Even if event happens, probability of E3 remains same. Similarly, you can do vice versa as well. Probability of even given E3 has already happened. That will also be equal to probability of E1. Okay, independence works both ways. So yeah, E1 and E3 are independent. Now probability of E2 intersection E3 is what? 0. Is it equal to probability of E2 into probability of E3? No. Probability of E2 into probability of E3 is 1 by 54, which is not equal to 0. So they are not independent. Okay, E2 and E3 are not independent. Actually, E2 and E3 are mutually exclusive. They are exclusive. They don't have anything in common. You cannot get a sum of 5 and a sum of 7. E2 and E3 are mutually exclusive. We will see later that if there are 2 events with non-zero probability and if they are exclusive, they can never be independent. It's a proof as well, right? If they are mutually exclusive, their probability of intersection will be 0. And if the individual probability is not 0, they will never be independent, right? If 2 events have a non-zero probability and if they are mutually exclusive, they can never be independent, right? So E2 and E3 are exclusive, not independent, and E1 and E3 are independent. These are the 2 relations that we have. Okay, cool. Let's move to an example. So an urn or a bag contains 3 green and 2 red balls. You take out 2 balls with replacement. So here this is important. By default, if nothing is mentioned in questions like these, you don't assume that you are replacing ball. Let's say someone is saying that there is a bag and you take 2 balls out of it. By default, if nothing is mentioned, you are not replacing the balls. You take 1 ball and then you take the second ball. You are not replacing. But if it is mentioned, and read it very carefully, okay? Read the problem in probability very carefully. I made this mistake in GATE as well, right? So, if very carefully with replacement, there is very small like buffer, okay? I made it bold here. In the paper, it won't be bold, okay? So read it very carefully. So it is mentioned that you're pulling 2 balls with replacement. What does it mean? You'll take 1 ball out, then you will see the color, and then you'll again put it back. Again shuffle and again put 1 ball out. So the state of bag remains same after pulling 1 ball out, okay? So you take 2 balls with replacement. So what is the probability of getting a green and then a red ball? So easy problem. So a bag contains 3 green and 2 red balls. Okay. So see here what happens. You take the first ball and then the second ball. It is very obvious that these events are independent. Okay, some like when you solve many problems, okay, when you solve a lot of probability problems, you won't even need to use the formula. You can use the formula here, but it is very obvious that getting a green ball, so let's say event E1 is this, getting a green on the first ball, and event E2 is this, getting a red in the second trial, getting a green and then red. So it means that event E1 is getting a green on the first trial, and then E2 is getting a red on the second trial. Events E1 and E2 are independent of each other. It is very obvious, right? It doesn't matter what color happens in the first trial, probability of getting a red ball in the second trial will still remain same because you are doing it with replacement. Because you are doing it with replacement. Since you're putting the ball again and you're shuffling it again, the bag remains same. It will still have 3 green and 2 red balls. So it doesn't matter what happens in the when you pull out the ball in the first time, right? Probability of getting a red ball in the second time still remains 2 by 5. So these two events are independent. So what do you want? You want probability of E1 intersection E2, right? You want a green ball in the first trial and then you want a red ball in the second trial. You want E1 intersection E2. So it will just be probability of E1 into probability of E2. Which is, what is the probability of getting a green ball in the first trial? It is 3 by 5. What is the probability of getting a red ball in the second trial? Again, the state of bag remains same. So it will become 2 by 5. Right? So this becomes 6 by 25. Okay. Now second case is getting both green balls. So it will still be the same. Let's say E1 is the event of getting a green in the first attempt and E2 is getting a green ball in the second attempt. So probability of E1 intersection E2 will be what? Probability of E1 into probability of E2. So in the first attempt it is 3 by 5. In the second attempt it is again 3 by 5. So it is 9 by 25. Right? Cool. So okay, we can solve these problems, both these problems, without replacement as well. Let's say the question was without replacement. So now the events are not independent. So here in the first case, what will happen? What do you want? Getting a green in the first ball and then red in the second ball, second attempt. So what is the probability of E1 intersection E2 now? Since they are not independent, what we will do? Probability of getting a green ball in the first attempt times probability of getting a red ball in the second attempt, given that we got a green ball in the first attempt. We already saw in this in last class, right? Multiplication theorem. Okay. So what is the probability of getting a green ball in the first attempt? It is 3 by 5. Now, if you have got a green ball on the first attempt, now the bag will have what? 2 green and 2 red balls, right? If you already got a green ball in the first attempt, now you will have 2 green and 2 red balls. So now what is the probability of getting a red ball given that E1 has already happened? It will be 2 by 4. Okay. So it will be 3 by 10. So had it been you were pulling out balls without replacement, this is the probability. If you're doing it with replacement, this is the probability. Cool. So we have another question. There are 3 bags containing 3 red, 2 green, 3 red, 5 green and 1 red, 4 green balls. If you draw 1 ball from each bag, what is the probability of getting a green, red and green ball from first, second and third respectively? Again, so this, let's say event E1 is getting a green from the first bag, E2 is getting a red ball from the second bag, and E3 is getting a green ball in the third bag. Now it became very obvious. These 3 events are independent of each other. It doesn't matter what ball you are getting from the first bag. Probability of getting a red ball from the second bag doesn't change. Right? They are independent. 3 independent workers are working on these 3 problems. Again, see, there is a difference. These events are not exclusive. Exclusive events means what? Ki these 3 events cannot happen together. They can happen together. You can get a green from the first bag, red from the second bag and green from the third bag. So they are not exclusive. They are independent. Which means that it doesn't matter what ball you get in the first bag, the probability of getting a red ball in the second bag remains same. It remains same, right? So what is the configuration given? The first bag contains 3 red, 2 green balls. Second bag contains 3 red, 5 green balls. And the third bag contains 1 red and 4 green balls. So now you want green from the first bag. So the probability is 2 by 5 times red from the second bag. Probability is 3 by 8. There are 3 red balls and total 8 balls. So probability is 3 by 8 times probability of getting a green ball from the third bag. So there are 4 green balls and total 5 balls. So 4 by 5. Okay. So it's 3 by 25. I hope you got it right. Probability of E1 intersection E2 intersection E3 is what? Probability of E1 into probability of E2 into probability of E3. Okay. Now second problem is slightly tricky. It says that what is the probability of getting 2 green and 1 red ball? It is not saying, this problem is not saying that which color ball is getting pulled from which bag. It is just saying what is the probability of getting 2 green and 1 red ball. That's all. You can get it from any bag. So here you have to remember the rule of sum, which is like the very first lecture of counting. Okay. So again, what is the configuration? Like we have 3 bags. Bag 1 contains 3 red, 2 green balls. Bag 2 contains 3 red, 5 green balls. And bag 3 contains 1 red, 4 green balls. This is bag 1. Bag 2. This is bag 3. Now you want 2 green and 1 red ball. So either you can get green from here, red from here, or you can get a green from here, red from here, and green from here, or you can get a red from here, green from here, green from here. So the total task T is doing task T1 or T2 or T3. Whenever you have or, it is rule of sum. So either you get this or this or this. Your condition satisfies. So what is the probability of green, green, red? We already know. It is 2 by 5. Probability of getting a green from the first bag. It is 2 by 5. Probability of getting a green from the second bag. It is 5 by 8. Right? 5 green balls, total 8 balls. What is the probability of getting a red from the third bag? 1 by 5. Plus, since it is an OR, plus, what is, again, like you can do this now, right? Like it's very simple. Like probability of getting green from the first bag, 2 by 5. Probability of getting a red from the second bag, it's 3 by 8. Probability of getting a green from the third bag is 4 by 5. Plus, probability of getting a red from the first bag is 3 by 5. Probability of getting a green from the second bag is 5 by 8. Probability of getting a green from the third bag is 4 by 5. So you can just calculate this. This will be your answer, okay? So I hope you got it, right? Like here the configuration was not given. So we just applied the rule of sum. And here like we are applying the independence rule many number of times, 3 times. Since we know that getting different balls from these 3 bags is independent of each other, we are just directly multiplying the probability. Cool. Let's see another example on independent events. So a card is selected at random from an ordinary deck of 52 playing cards. If A is the event that the selected card is an ace and H is the event that it is heart, are A and H independent? Okay. So one card is selected randomly from the deck of 52 playing cards and A event is given as getting an ace. See, generally like in JEE, like in all exams, where aptitude questions are asked, like GATE, GRE, okay, and CAT, it is assumed that you have basic knowledge of a few things like rolling a die, coin. They won't explain like what can happen if you roll a die. The most tricky part is like remembering the shuffle deck of cards, okay? Generally, people don't remember that. If you have not played cards very often in childhood, like it will be difficult for you, right? Like so, then you have to remember, and they will assume that you have this knowledge. So whenever before going to exam, just know there are 4 suits in a standard deck of cards, and there are 13 playing cards of each suit. The 4 suits are clubs, diamonds, spades and hearts. There are 13 cards numbered from ace, 2, 3 up to 10, and then jack, queen, king, right? Jack, queen and king are called face cards. So just a quick refresher. So there are 4 suits: diamonds, hearts, clubs and spades. Okay, and diamonds, hearts, clubs, spades. Clubs and spades are black in color. Diamonds and hearts are red in color. Okay, and in each of the 4 suits there will be 13 cards each. Ace, 2, 3 up to 10. So 10 cards are like this, and then jack, king and queen. Jack, queen and king. Similarly, you will have the same configuration for hearts, clubs and spades as well. So 13 into 4, 52 cards, right? And these 3 are called face cards: jack, queen and king, because they will have a face on them. Jack will have a jack face, queen and king. Okay, these 3 are face cards, remaining are normal cards. And this is what happens. Okay, so they will assume that you have this basic knowledge. Okay, just a refresher. So event A is getting an ace, event H is getting hearts. Cool. So what is the probability of getting an ace? What is the probability of getting an ace? There are 4 aces, right? There will be an ace of diamonds, ace of hearts, ace of clubs, ace of spades. There are 4 aces, so 4 by 52. There are 52 cards, you can get any one of them. There are 4 aces, so probability is 1 by 13. Right? What is the probability of event H? H is what? Getting hearts. How many hearts are there? 13. There are 13 hearts, right? So out of 13 you can pick out any one of them. So probability of getting a hearts is 1 by 4. And now what is the probability of A intersection H? A intersection H is what? You are getting an ace and hearts, which means there is only one card which is both ace and hearts. It is ace of hearts. Okay, there will be a card called ace of hearts. So you can get only that card that is both ace and hearts. So that one card you have to get. So 1 by 52. So is probability of A intersection H equal to probability of A into probability of H? Yes, it is. It is 1 by 4 into 1 by 13. It is equal to probability of A into probability of H. So yes, A and H are independent. So you see that as well, okay? Logically as well, it is correct. Event A was getting an ace. Event H was getting hearts. So what is the probability of getting an ace initially? It was 1 by 13 because there were only 4 ace cards. It was 1 by 13. Now event H said that it is definite that you are getting hearts. So it doesn't matter if you are getting hearts, then also probability of getting an ace is 1 by 13. Since now you have reduced the sample size to 13 cards. Initially it was 52 cards and 4 were aces. But now it is 13 cards and only 1 is ace. So probability doesn't change. It is still 1 by 13, right? So probability of A given H has already happened, won't change. Similarly, probability of H given A has already happened, won't change. That's why they are independent, okay? Cool. So there are a few axioms. If A and B are independent, prove that these events are also independent. Okay, these are very important actually. These are very important, we will see. If A and B are independent, then A and B complement are also independent. Basically, you take complement anywhere, they will still be independent. A and B complement, A complement and B, A complement and B complement, all of these will be independent. This is a very important theorem. Okay, they can ask you this in multiple correct type questions, or GATE doesn't have that, then you'll get a very beautiful MCQ on this. Okay, and these type of questions are most tricky questions, trust me. Because formula you can apply anytime. They are not directly formula based. You have to prove it. If A and B are independent, are A and B complement independent, okay? And their proofs are also not very trivial. So we will see that. Given that A and B are independent, what does it mean? Probability of A intersection B is equal to probability of A into probability of B, since A and B are independent, okay? Now what does it mean? This is the Venn diagram. A and B. So probability of A intersection B is probability of A into probability of B. This is given. Now you want A and B complement. So this is the set that you want. So basically you want this set, A intersection B complement. It is A intersection B complement. So these are the elements, white shaded area are the elements which are in A but are not in B. Right? A and B complement are in A but are not in B. So how will you get this set? See, one thing is very clear, that this white area plus yellow area is entire A. White area plus yellow area is A. White area and yellow area are mutually exclusive, and their sum is equal to probability of A. So we can use that. Probability of A is what? Probability of A is probability of A intersection B complement plus probability of A intersection B. You have to agree on this, right? Since A intersection B complement is this area, A intersection B is this area, probability of A is what? Probability of A intersection B complement plus probability of A intersection B. So what does it mean? Probability of A is probability of A intersection B complement plus probability of A intersection B is probability of A into probability of B. So here if you take this to LHS and this to RHS, you will get probability of A intersection B is what? A intersection B complement is what? Probability of A you can take out. It will become probability of... Okay, here you will have to shift this side. Okay, so it will become... Okay, yeah. 1 minus probability of B. Okay, you can rearrange. It will be very easy. You have to take this entire term this side. So what does it mean? Probability of A intersection B complement is probability of A times probability of B complement. We know that 1 minus probability of B is probability of B complement. So hence proved. Since probability of A intersection B complement is probability of A times probability of B complement, A and B complement are also independent of each other. Okay, and similarly, like these two problems are symmetrical to each other. Instead of this area, if you take this area, B intersection A complement, you will get this theorem as well. Okay, consider this homework. Okay, like if you take this area, this will also be proved. This is slightly tricky. So here you want A complement and B complement. So how will you prove this? So here the Venn diagram looks like this. A, B. You are given this area, but you are interested in some other area. You are interested in A complement and B complement, which means the elements which are not in A and they are not in B, which means this area. These are not in A and not in B. So how will you get this? So it is very obvious that probability of A intersection A complement intersection B complement is what? See, the set A complement intersection B complement is nothing but A union B complement, right? It's a form of De Morgan's law, right? This is A union B. A union B is all this area. Whatever is not in A union B is not in A and not in B. So this is true. So probability of A intersection A complement intersection B complement is probability of A union B complement, which is what? 1 minus probability of A union B. Okay, and we know that what is probability of A union B? You just expand it. It is probability of A plus probability of B minus probability of A intersection B. We know this. Okay, inclusion, exclusion. So this is what it is. Okay, so what do we want? Okay, we want to expand this only. We want this to be proven to be probability of A complement into probability of B complement. So what is this? It is 1 minus PA minus PB minus P A intersection B plus PA intersection B, and PA intersection B is nothing but PA plus PB. So plus PA into PB. So this entire term is nothing but 1 minus PA into 1 minus PB. Right, if you multiply these, you will get these 4 terms. So this is nothing but P of A complement into P of B complement. So hence proved. Since probability of A complement intersection B complement is probability of A complement into probability of B complement, A complement and B complement are also independent of each other. They will all be independent. Okay. Cool. These type of these examples will be useful in these type of examples. So if two people A and B are interviewing for a job, and the probability of their selection is this. So probability of selection of A is half, probability of selection of B is 1/3. So what is the probability that? What is the probability that both of them are selected? So we are given that probability of selection of A is 1/2 and probability of selection of B is 1/3. Okay, obviously they are independent of each other. Given that A is, nothing is mentioned, right? So it is just said that probability, so here you have to assume nothing is given, so definitely they are independent of each other, right? Probability of selection of first guy is half, 50%. Probability of selection of other guy is 1/3. If first guy gets selected, it doesn't matter, like it doesn't matter, right? The probability of still getting selection of second guy is still 1/3. So they are independent of each other. So what is the probability that both of them are selected? It means probability of, so let's say event even is, okay, we are already given events A and B. So if, what is the probability that both of them are selected? It is like probability of A intersection B. A is selected and B is selected. So it is probability of A into probability of B, 1/2 into 1/3, 1/6. Exactly one of them is selected. Exactly one of them is selected. It means that A gets selected and B is not selected, or B is selected, A is not selected. A is selected, B is not selected. Exactly one of them. Or, so again we have an OR, rule of sum. So we already know that if A and B are independent, A and B complement will also be independent, right? See, it is very logically interpretable as well. If happening of B doesn't, basically what does it mean when we say A and B are independent? Ki if B happens or not, probability of A will remain same. So that's what it is, right? If B happens, probability of A will remain same. If B doesn't happen, then also probability of A remains same, right? So A and B are independent, then A and B complement are also independent. B happens or not happens, doesn't matter, probability of A remains same. So these two are also independent. So what is the probability of A getting selected and B is not selected? It is probability of A into B complement is 2/3, or means plus B is selected 1/3 and A is not selected, it is 1/2. Okay, so it becomes 3/6 or 1/2. Exactly one of them gets selected. And third is, at least one of them is selected. At least one of them is selected. What does it mean? Either A is selected or B is selected or both are selected. So there will be 3 cases. Better is you just do 1 minus none of them selected. There are 4 cases, okay? Both are not selected, A is selected, B is selected, and both are selected, right? Here you want at least one of them to be selected. So it is nothing but 1 minus none of them are selected, which means 1 minus A is also not getting selected, B is also not getting selected. So it is nothing but 1 minus, what is probability of A not getting selected? 1/2. What is probability of B not getting selected? 2/3. So 1 minus 1/3, it is 2/3. So 2/3 is this, 2/3, 1/2 and 1/6. Okay. Cool. So this concludes this slide. We will have one more lecture on independent events. We will see independence of 3 events and a few axioms on that, and a few examples which are already asked in GATE. Independent events is a big topic. Most of the questions in probability comes from conditional probability and independent events. That's why we're taking a long time in learning this. So we'll solve a lot of examples in the next class, and we will see a few more theorems. Cool. Thanks. Bye.